Okay, so today we embark on a slightly more, I would say, demanding part of the course. It is demanding not because it is particularly difficult or because it has to be difficult. Rather, it is demanding because the language is going to be new and unusual. All right. We are going to encounter something called Laplace transform and transfer functions. For you, if you have been lucky enough, you had Laplace transform as part of differential equation course. But my experience tells me that almost always you require sort of to learn it anew. Simply the context in which we use Laplace transform in those two courses here in differential equations is significantly different. So somehow you have to learn it. That just comes from my experience, but possibly I'm wrong. All right. Now, why do we need this part of the course? First of all, until comparatively recently, by which I mean until the last 30 years, the entire control theory was done in transfer functions, in what we call frequency domain, right? In Laplace domain. That was the main instrument for everything. Because of that, a lot of literature, a lot of ways we think about control problems, a lot of ways in which we talk about control problems are formulated using transfer functions and Laplace transform, like Laplace domain. So for you not to know it would be a great impediment. You wouldn't be able to interact with a lot of older style ideas, literature, and so on. And since this goes forward, like those terms don't go away, new generation of people still use those old terms. It would sort of be just a burden on you, right? You can do control theory completely without Laplace transform and without transfer functions, but it is burden for no reason. It is not very difficult to understand this part of the topic, and it is important because people use it. That is the reason number one. Reason number two, it is going to give us a few very good tools, even on the introductory level, as we are going to study it. We are going to spend basically like 2.5 lectures here. It is going to give us very good tools, which are very hard to match using anything outside of Laplace transform. All right. So there is a very good reason to do it, but at the cost of learning sort of like a new language of thinking about differential equations and control. All right. So let's embark. Our attention for today is going to be to try to get what is going on, try to understand the representation. Okay, so we can begin. So first of all, there is this idea of a Laplace transform. Right? Mathematically, it is given by the expression here, expression 1. Let's try to understand what is in this expression. So what we are saying is there is a function f of t, is a function of time, right? F of t. We can transform it by putting it in the integral, right? So you can see it is inside the integral. Integral goes from 0 to infinity, right? Together with this function, under the integral, there is a kernel. This e to the power minus st, right? And the integral is taken by time, right? It is a time integral. Now, what's going to happen after you take this integral is time is going to disappear, right? You took this integral from time equals 0 to time equal to infinity, right? And after you take it, time went away from the function. But there is a new variable that you introduced, this variable s. This variable s happens to be a complex variable. So as a result, you would have a complex valued function of a complex variable, s. And this function is called image of the Laplace transform, right? So that's what's going on, right? That is what is called Laplace transform. Now, this sounds to you, depending on your perspective, may be completely wild and strange. Maybe it reminds you of Fourier transform. Maybe it just reminds you of general idea of such transformations, integral, function, kernel. This is not really all that strange. This in mathematics happens quite often. But I think regardless of the perspective, you would still see it as a little bit scary. There's a massive formula right here. All right. Okay. This transformation gives us more or less a whole separate field of mathematics. Mathematics of those Laplace images, right? You can have entire course just on that. And this mathematics is very interesting. There is a lot of details there. We're going to spend comparatively little time in this course on this material. So by necessity, we're going to sort of fly over a lot of the details that are interesting mathematically. I want you to keep in mind that those details exist. They can be easily found in courses, in textbooks, and so on. We will try to be more utilitarian, but we will take what is actually useful. But by no means are we going to exhaust the topic. All right. Okay, so this is the definition. Now, our reality of using Laplace transform is not going to be as scary as the definition. But let us start by using this definition to derive one particular image of a function. And the function we are going to work with is dx dt, right? Dx dt is a function of time for some kind of x. So if x itself is a function of time, dx dt is also a function of time, right? Let's find its Laplace transform, okay? So Laplace transform, I will denote it by this, what do you call it, calligraphy L, right? And this is the function which we are trying to transform. Okay, so by definition, as I was saying earlier, Laplace transform is the function itself under the integral from 0 to infinity with the kernel e to the power minus st. Integral is taken by dt, right? So far, so good. What we're going to do with it is we're going to take the integration by parts. Let me just sort of mechanically remind you what integration by parts looks like. Here is the formula. So integral of expression where you have v times du dt, right, is the same as v times u minus a new integral. And this new integral is, sorry, I will try to color code just so we can keep track. dv dt times u, all right? So basically what happens with this formula is we can, if you allow me, switch around which variable is going to be differentiated under the integral. So originally it is v times du dt. After the integration by parts formula, what we have is dv dt times u. And we have this expression outside of the integral now. All right. That is the just formula integration by parts, right? Now, what I'm going to do is I'm going to denote du dt to be dx dt, right? From this formula here. Okay. U is therefore x, right? U therefore is x. Now, what is v? Well, v then has to be whatever is left, right? Like if du dt times v is what we have under the original integral. So it has to be e to the power minus st, right? So that is what v is. And what is dv dt? Well, we just take a derivative of e to the power minus st, derivative with respect to time. So s and minus goes outside of the exponent, and the exponent stays the same, right? So far, seems clear. Now, we need to assemble it in the order as represented by the right-hand side of this expression here. That's what we need to do. Like, we need to recreate this assembly. Right, let's do it. So v goes, here, right? Where let me be careful. So v is e to the power minus st. It goes here, right? Here. Next to it, we have to have u, which is x. Here it is. Minus, same as in the formula. And then we have dv dt, right? Which in our case is this expression. So minus s times e to the power minus st. So let me just keep the color coding correct. Right? That is the expression. Times u. Right? Times u. Okay. All right. Now, I think you were able to follow what I did with how expression 2 became expression 4, right? If not, please ask me. Okay. Now, here's the key idea. Here's the key idea. What we have in the integral here is basically, if we take this s outside of the equation, put it here, right? We would also have this -1 will become plus, and this goes away. Right? And what we are left with under this integral is the kernel function. Let me, I guess, highlight it. Kernel function here times a function of which we take Laplace transform, integrate from 0 to infinity over time. So what we have under the integral is just a Laplace transform of x, by definition of Laplace transform. So because of this clever integration by parts, we were able to get everything out of the integral, and what was left in the integral is just a Laplace transform, became just a Laplace transform of x. So with that, I would be able to call all of this to be L of x times s, right? That's what happens. Now, we also have to understand what happens here. That is quite straightforward. So first of all, we have behavior of this of those constants at two different times, at 0 and at infinity. So at 0, and in terms of t, of course, right? T. So at 0 and at infinity in terms of t. Right? So when t is equal to 0, all of this is equal to 1. Right? So this whole expression becomes x at 0 with a minus sign because there's a lower bound of the integration, right? Okay. Now, when we're talking about t at infinity, right? What happens is this becomes minus infinity. E to the power minus infinity is 0. So x multiplied by 0 is 0, right? So what we have is 0 minus x of 0 plus this guy. That is the formula. All right. I apologize for not using stuff like limits. Of course, we would have been more correct if we cast all of this with additional variable, some a that tends towards infinity, and therefore the limit itself tends towards 0, and so on and so forth. I apologize. We're trying to be faster, so there will be a lot of those small details which are going to be lost. But you had a rigorous course of analysis, so you would be able to substitute those details where I leave them off. So I just trust you to, be able to fill the blanks. Okay. So with that, what we have is expression for our Laplace transform. Apparently, Laplace transform of dx dt is just minus x at 0 plus s times Laplace transform of x. That's not all. Let's do one more step. Next step is a convention. In control theory, where we use Laplace transforms, we always assume that initial conditions for differential equations that we transform are 0. So all our differential equations will be assumed to have 0 initial conditions. With that, what we have is Laplace transform of x. If we define it as big X of s, by the way, big letters here, convention. For Laplace transforms, we prefer to always use capital letters. So with that, what we have is if we define Laplace transform of x as big X of s, right? Then Laplace transform of dx dt becomes s times Laplace transform of x, or in other words, s times x of s. Let us just spend a couple seconds admiring how beautiful it is. We had a derivative, right? Now, derivative in Laplace image of a derivative is just a Laplace variable times the function, right? So if the function itself is x, derivative of this function is s times x. Is great. And notice how fast the difficulty dropped. So originally, we looked at this tremendously scary formula, right? Very intimidating. Now, what we are looking at is that derivatives become just a multiplication by additional variable. Much easier. That is the theme of Laplace transformation. It is quite easy in terms of direct usage. As long as you understand what you're doing, it's quite easy. All right, let's apply this in practice. I understand right now, maybe you have like questions and so on, right? So they are maybe even difficult to articulate. Let me show you how we apply it, and it will become, I think, much clearer. So let us try to look at the differential equation y double dot plus ay dot plus by equal to u, right? Where u is just an input, right? Input of time. Very reasonable differential equation. We have seen those many, many times already. Let us try to find Laplace transform of both sides of this equation. When we transform the functions themselves, such as y, for example, we will just replace it with capital Y of s, right? When we transform u, we will replace it with capital U s, right? Okay. So now let us try to understand how this Laplace transform will work. So first of all, I will start with right-hand side and then go left. Transformation of u. Well, that is just capital U of s. Transformation of b times y. Well, this is b times y of s, capital Y of s, right? Why can we take the constant out of the equation? Well, because it is linear, right? We can take the constant out of the integral. When we performed all our operations, we could have taken the constant out, and everything will be the same but multiplied by a constant. So the operation is linear, basically, because of integration being a linear operation. So we could just take the constant out, right? Same as we can take a derivative of the whole right-hand side separately because this linear operation, right? We can split integral of a sum into sum of integrals. Okay, so b of y, image of this transformation will be b times y of s. Now, this thing here, a times y dot, that is where we encountered derivatives for the first time. So this a times s times y, capital Y, right? So this dot here becomes this s here. That is what happens. We have a derivative, becomes s. Now, lastly, what I will claim is that y double dot will become x s squared times y, capital Y of s, right? Just think about it just for a second and see if you agree with me or not. Hopefully, it makes sense. Of course, if you want to argue about it, I guess what you could do is, for example, to say that let P be equal to y dot, right? So if we want Laplace transform of dot P, we know that there is going to be something like S times P of S, right? But then if we want to have a Laplace transform of y let me put it like this. If we want a Laplace transform of y dot, right? It's going to be s times y of s, right? But this also has to be, by extension, because of the first equation, the Laplace transform of p. So p of s. And with that, what we get is Laplace. This formula becomes now. Wait, 1 second. I will just move it. So okay, this formula now becomes something like this. So instead of p, we substitute here this guy, right? And voila, that's what we get. That is again, I'm gliding along, not trying to be very rigorous with my derivations, but the essence of like how you can try to derive it seems to be clear from what I showed here, right? So your double dot will become just s squared, okay? Triple dot will become s cubed. So derivatives, how many of them? If it is fourth order derivative, you get s to the fourth power. Nth derivative will become s to the nth power. All right. Now, magic didn't stop. so far we only were able to transform this equation into this very nice form. But that is not enough. That's not all that we can do here. What we can do next is we can take these guys and put them outside of the brackets, right? So in the brackets will be s squared plus as plus b, all multiplied by capital Y s. And then what we can do is we can express what capital Y out, right? So capital Y can be expressed out. And what it would give us is 1 over this expression that was in the brackets, right? So 1 moment. 1 over this expression, right? Here it is. Multiplied by capital U. So our differential equation somehow became a fraction. Like the form of differential equation is now a fraction. This guy that we showed here, this guy, is a transfer function. We call it a transfer function. And this whole thing is a transfer function representation of a differential equation, right? The whole idea of a transfer function is that it maps input to the output. Now you remember the first lecture in which we had equations like that. And when we were discussing state space representation versus ODE representation, I mentioned that like y here somehow, should be considered an output of the equation. That somehow makes sense when you consider ODE, right? Because you don't, unlike state space where you have separate equation, y equals to cx, here you don't have a separate equation. So it would make sense if your differential equation variable is itself the output that you are seeking, right? So in this sense, here, capital Y is your output, capital U is your input. Just as here, Y is your output, U is your input. And transfer function is what maps one of them to the other. So that's your transfer function. It is mapping your input to your output, right? You simply multiply your input by the transfer function, you get output. But in the Laplace domain. So all of this happens in Laplace domain, not in time domain. Any questions so far? Okay. So let us just do a couple examples to solidify our understanding. So let us consider this differential equation. Here, how can we find its transfer function? Well, we know that downstairs here, we would have basically this expression after we replace all the dots, all the derivatives with s, and then take capital Y out of the brackets. So let's do it, and let's see what happens. So first of all, this would produce for us 2 times s cubed, right? That's what's going to happen here. It's going to be 2 times s cubed times capital Y, but capital Y goes out of the brackets. So 2 times s cubed, that's what's going to give us. This is going to give us 5 times s. This is going to give us minus 40, right? So let's see, 2 times s cubed, 5s, minus 40, right? This guy, when we do a Laplace transformation, would remain s. There is a question in the chat. I will answer just in a second. And then it stays here. Right, let me see it. Moment. What does it mean to have input in the Laplace domain? What does it mean to have input in the Laplace domain? All right. That is a tricky question because somehow what you're asking is intuition, what input means. Right? It's a good question. It's not easy to answer. I'll try my best. Right. So this guy here and this guy here are both signals. All right. They're signals. So what is a signal? Right. For example, a signal can be a control input from your pilot. Let's say you have an airplane, you have a pilot that pilots airplane. I don't know, like maybe with a whatever you would have given to the pilot to give instant commands, right? Let's imagine this is something like a joystick. So the pilot gives commands to the airplane, right? It produces a sequence of numbers, right? Sequence of values. Could be electric current, could be a sequence of numbers going through digital control system, but it is a signal, right? We can think of the signal as existing in the time domain, right? That for us is very natural. We would think of the signal as a profile that changes with time. That way of thinking gives us this u of t, right? Signal as a function of time. Alternatively, for any of you, especially who have thought about sound and how we record sound and so on, you can think of a signal as a combination of harmonics, combination of sinusoids, right? Like various profiles of harmonic signals. And then you can consider it, roughly speaking, as a spectrogram, as a what kind of harmonics exist in the signal. That will be frequency representation, right? This, I think, makes some kind of sense. Frequency representation, right? You're thinking of signal as what kind of harmonics does it have? It has this very low harmonic, as for example, the pilot goes down, then after a while up, right? Then there are a lot of very much smaller harmonics which relate to like some trembling in his hands and so on, right? So you would have a combination of harmonics. And obviously, the pilot doesn't give you a sinusoidal input. He gives you, for example, like a square input. But if you studied, signals, you would know that any function of time can be approximated by an infinite sum of harmonics, right? So for us, somehow it is meaningful to think of a signal not only as a signal of time, but also as a signal of frequencies, right? Laplace transformation of a signal gives you something like that, except it is not just frequencies, but also the speed at which those frequencies die off. That is like my intuition about it. It's not, it's not from the textbook, right? But the way I prefer to think of Laplace frequencies is Laplace signals is, sort of like a frequency representation, where your signal is just a combination of sinusoids at various frequencies, summed together to give you a original signal, but also is the speed at which those signals die off, right? That is my intuition about how to think about Laplace signal. Why this is so? I I would hesitate to try to answer right now. It would require a little bit more mathematics and stuff like that. But if you think, instead of thinking about it the way I just discussed, if you just think of it as combination of frequencies, you intuition wise you would be right there. Like there wouldn't be any problems. So you can just think of it as it's called frequency domain in many textbooks, like the recommended textbook for this course. They call it frequency domain, right? So you can think of it as just frequencies. So it's not a signal in time, it is signal in frequencies. So we're not thinking about how it evolves over time. We're thinking about it how it evolves over different frequencies, right? Something like this. If this is okay with you. This is okay with you. Let's now say that it's not okay with you. Let's say that this is nebulous and not very good, and it does give intuition. What is good is that you don't need this intuition because you're not going to analyze signals in Laplace domain. What you're going to analyze is only transfer functions. So what is important in our studies is going to be this. We are almost never going to directly look into this guy or into this guy. It's always going to be this guy, right? And this analysis of transfer function will be perfectly sensible. There wouldn't be any nebulous, to an extent, there wouldn't be nebulous parts there, right? So even if you don't have intuition of what this means, right, it is okay. I would argue it's not terrible. You need intuition about this, not about this. Right. Hope I answered the question. Let us continue. So next we consider this ODE. Relatively simple. We're going to do the same thing. We'll look here. We have 2 times y dot. So y dot will give us s, right? So 2 times s. Here it is. Here's minus 4y. It's going to give us minus 4. So minus 4. Here's a 1 in front of u. So this is a 1. And that's it. So we got a transfer function just like that. Last example. Here we have 3x triple dot, y triple dot plus 4y equals to u. Right? So this would give us 3 times s cubed. Right? Oh, sorry. Here, 3, it should be 3 here as well. 3 times s cubed plus 4. Oh, plus 1. Upstairs, there's a 1 because nothing is in front of you. Is it clear how we construct transfer functions from differential equations? I think it is relatively clear, right? If I wanted to oversimplify the course, what I could have told you is, like we could have ignored Laplace domain altogether. What I could have told you is we introduce a derivative operator, which is making y dot into p times y, right? Y triple dot into p cubed times y, right? Derivative operator. And, do the same thing, basically. And it will give you the same results. And that is, in a way, reasonable thing to do. So you can see it is, this operation is quite mechanical. It mostly just tells you to look at the derivative, how many derivatives you have of this variable, replace it with so many s variables, and that's it. You get denominator and numerator of your transfer function. Okay, all right. Now, what it also allows us is to consider more complicated looking ODEs. So consider this ODE. It's a little bit strange, right? It is strange because of this guy. Like this, for us previously, it would have been a little bit suspicious. Like we would have asked, what exactly does it mean? Of course, what it means in terms of time domain is that we have an input signal. It is differentiated, multiplied by 10, and the sum of this differentiated multiplied by 10 and the original signal multiplied by -1 is what you input. So if your original input was, let's say, um, um, your original input was current, you take a derivative of a current, right? You multiply it maybe by inductance, and the sum of all of this is somehow what acts on your system, right? As producing torque, for example, right? Uh, okay, or maybe something else, producing some kind of measurement. So this is not crazy as an idea that not only the input signal would act, but also the derivative of the input signal would act. In fact, when we considered PD control, somehow there was like KD, you remember KD times um, X dot, Y dot plus KP times Y, right? So the fact that input has a derivative is not totally out of the blue, right? If you remember last lecture and the spring mass damper system. But it looks strange when you look at this as an ODE. Now, in Laplace domain, uh, this is completely natural. So what we do again is we transform the right-hand side. Let me do it. So we have 2 times s squared, right, from this, plus 3 times s from this, plus 2 from this. We transform the left-hand side. Now we have 10s times capital U from this, minus capital U from this. That's it. We put, both sides in a form where U is taken out of the brackets, capital Y is taken out of the brackets. So just as before, nothing new. And then we express Y just as before. We express output. So we put everything into the right-hand side. So here's this becomes denominator, right? This becomes numerator. So what is interesting here is the transfer function is still a fraction. But now in the numerator, we don't have just a constant, we have the expression of Laplace variables. But ultimately, this differential equation here, it looked a little bit strange to us because we're not used to this type of differential equations, I guess. Right? But when we consider it in the form 13, still we have a transfer function times input giving us output. So somehow it shouldn't feel strange. I mean, not much stranger than the other transfer functions that we have seen, right? That is one of the powers of this Laplace representation, transfer function representation. Some of the things that look a little bit off in the time domain look much more natural in the Laplace domain. We will explore this in just a little, just a second. Okay. Now, let us consider control law from the last lecture, PD control, right? So proportional part, differential part, PD control. We can find transfer functions with control. The transfer function would look like minus KD times S from here, minus KP from here. I put minus up front. And here is your input. In this case, for the control law, the input is Y, right? The output is U. Because what is going into this equation? What are you trying to find? You're trying to find U, right? You get Y as input. So that is your transfer function for the control law. So we can do this as well. If we have a control law, we can also represent it in Laplace domain. Okay. Now, since we learned so much about our state space systems, it would be a little bit unfortunate if we could not use systems that are given to us in the state space when we are trying to apply our Laplace transform methods, right? it would be unfortunate if we are stuck with um, if we are stuck with um, using only ODEs when we want to do something in state space, or sorry, in transfer function representation. Lucky for us, that's not the case. We can easily go from state space representation to transfer function representation. In fact, that's absolutely natural and easy. How do we do it? Well, we know that here is the only derivative in this whole representation, right? What would be Laplace transformation of a derivative? It will be s times the Laplace transformation of the function. So this is how it's going to look like. Here, this is supposed to represent state space equation converted into Laplace form. So I guess maybe it would have been best if I put here like, those reminders that all of this is a function of s. Like this is a function of s. X is a function of s now. Like all of this is functions of Laplace variables, right? So after transformation, this is what happens. Now, what we can do is we can consider this first equation, right? Consider this first equation, and we can collect all the variables containing x on the left-hand side, which would be in our case, well, it'll be s times x minus ax. I mean, it's already done here, right? Minus ax. Then we can, equal to bu. What we do as the next step, we express x out of the put it out of the brackets, right? So we have identity here, identity times s minus a times x equals to bu, right? Next, what we do is we multiply everything by this guy inversed. Right? And that is what we have downstairs. So this is obtained from this equation by collecting x on the left-hand side, expressing it out. Right? Here's the steps. And next, all we need to do is to just substitute here. So we would have y times s times all of this plus d times u. D I only put here for completion's sake. It is called a feed-through term. In a lot of textbooks, you would find it. We're never going to use it in this course, but it is very easy to put it here. And I think, since it is everywhere, if I don't put it here, when you are going to start searching for those formulas, you will see dissonance. The formulas would look different for you in the textbook compared to what I gave you. So I put it here just for that. But in your cases, it is always zero. So, and not only in your cases, but almost always in practical work. Sometimes it is not zero, but it is a rare occasion. So almost always for what you're going to do throughout your study and even your research, you're going to see d equal to zero. So, you don't need to worry about it too much. But it's good to know that you can put something else there, not just zero. All right. So what after we substitute this guy into here, what we get is y equals to s, this s, c, sorry, y equals to c times all of this plus d times u. And now this is a transfer function. This is a transfer function. Okay. Right. So, and that is how you find transfer function. Now, let's say you forgot the formula. Like deriving this is easy. Like just take a piece of paper and a pencil. You can do it in 5 minutes. Good exercise, very easy. Means you don't have to apply to textbooks. Right? It's good. There was a question. Okay, no question. Right, so very easy, right? Very easy to do, um, easy to derive, and also, you can, if you want, you can look it up. It is a very simple formula to write, very simple formula to use, right? Look at it, very easy, and it is one formula for all state space systems. And you can imagine the state space systems are, numerous. A lot of things would be represented in the state space form. All ODEs can be represented in state space form. So this is more or less a formulas that you can use, especially if you want to automate production of your transfer functions. Just, always here, one formula for all cases. Previously, we were looking at how to do it sort of by hand. This is just a recipe for automation, more or less, right? Okay, quite easy, quite nice. Good. And now we have three representations with which we are going to work for the whole course. No more representations until the end, right? ODE representation, which you knew before, now you see it, in front of you. We have a little bit of more of this like m derivative of u, which is unusual, but you now can see, how it comes in, right? All of this. ODE representation. State space representation, very useful. You already have seen how we're using it for stability analysis, especially. And now you see transfer function representation. Now, since all of them represent one and the same thing, for example, a robot, a drone, a suspension system, thermostat, whatever else, they represent the same plant. It is nice to be able to talk about something like this without invoking a specific system. I would like to talk about stability, but not of a ODE, or not of a state space system, or not of a transfer function. And to be able to do that, you can call it a system, right? You can use this calligraphy letter to denote that it is a system, not a, for example, transfer function, right? Yeah, and you can talk about it as a system, right? System would have input, would have output, would have its stability properties, everything else. All of this is a system, right? All of this represents the same system, more or less, right? I mean, here's your input, here's your input, here's your input, your output, your output, your output, right? So it's the same system. And you can talk about it in terms of systems, right? In a lot of places, this is how people would talk about them, about properties of systems. Representations are specific ways to discuss systems, but systems exist outside of representations. Okay, good. Now, we have more time, and we need to cover quite a bit of ground. So I will talk slightly faster, but we'll see. You can see from the slide already there's a lot packed there. Don't worry, it's not very difficult. Okay. So let us consider a system like this, right? Y of S, sorry, equals to G of S times U of S, right? This is our transfer function. This is our input. This is our output. Now, for this system, we can do control law, which we, for example, designed in the time domain. Here is a time domain representation of the control law, right? It is a PD control. Here's a proportional coefficient. It is multiplied by a difference between a reference signal and current output. Here's a derivative coefficient. It is multiplied by a difference between derivative of the reference, derivative of the output. Reference we already saw in the previous lecture, where we talked about two things. One was the trajectory following, where reference was the trajectory that we try to follow. Another one was a new input idea, where we say we can replace original input for example, voltage to the motor with a new input, for example, with the desired angle for the motor. All right. So this is our PD control with a reference. Let us take a Laplace transform of this guy. So what's going to happen is when we Laplace transform of this guy, it will be just capital V, right? Okay, it's going to be multiplied by Kp. When we Laplace transform this guy, it's going to be capital Y. It's going to be multiplied by the same Kp. So we can just multiply this difference between capital V, capital Y with Kp, right? When we take a derivative of this guy, it's going to be S times Kd. Same with this guy. It's going to be S times Kd. And both are multiplied still by the same difference, V minus Y, right? So control law 22 in Laplace domain becomes control law 23. You can see that in a sense it is a difference between two inputs, but multiplied by a transfer function like that. Now we can call this guy here a controller H, right? The capital H of S. We can substitute it into here, since we know that basically U, right, becomes H times V minus Y. So U becomes H times V minus Y. We can open the brackets. We'll get here HY, right? Let me clear everything. So this will become this after we open the brackets, right? Minus Y times G times H. This is here, right? Now we put this orange expression into the right-hand side, and we take Y out of the brackets. So this guy is this identity plus GH, and we get this Y. Okay. This green expression still stays here. Now we can introduce a transfer function that would transfer input V to the output Y, right? And we get our denominator from here and our numerator from here, right? So what I did was basically I transformed everything into Laplace domain, right? It was quite straightforward. And then I just did manipulation to get it in the form Y as a function of V. So I replaced the original input, U, with a new input V. And here's the formula. Now notice that this formula is general. Like this H here is the controller that I decided to choose. I could have chosen different controller. As long as it can be represented as a transfer function, this formula stands, right? Because it's general, it's just for any control that depends on difference between the reference and output, this is going to be the expression. So you can see we easily generalize here, right? Which is quite good, Especially take notice of this denominator here, 1 plus G times H. This is going to come around quite a few times next step. So this is something to take note of. Now we'll consider one more example. Here we're doing it differently. We introduce a reference signal, which is going to be defined as Kp times V plus Kd times V dot. All right. So reference signal is somehow is a signal V multiplied by a number plus derivative of V multiplied by a number. And the control law would look like a reference signal plus our feedback control. As you remember from the lecture on stability, or on the stabilizing control, this is a typical feedback controller, right? It depends on the state. So here it doesn't depend on the difference between the reference and the state. It depends straight up on the state. But notice that this is exactly the same control law. If you open the brackets here, you'll get exact same control law as in the previous section, right? So actually it is the same thing. I did not change anything. This U is exact same control law, okay? But I called it now like a reference signal R, so it looks different. Okay, let's Laplace transform this expression. What we get is the same H times Y as before. It comes from transforming this expression here. Okay. Plus, let me do a color coding. Plus this R of S. That is the Laplace transform of the reference. So this H, you can see, what is this H? It is Kp minus SKD. Y is just from this Y. Right? Now we'll substitute this expression. Let me try to. So we get this expression. We substitute instead of into the, multiplied by G. Right? Our system, if you remember, is capital Y is equal to capital G times capital U. So instead of capital U, we substitute this guy. Right? So what we get is this component that has to do with this guy. And this component that has to do with this guy. Right? We do the same trick as before. Try to put everything with Y on the left-hand side. So this is what we do. Right? Everything else is on the left-hand side. So here's what left on the left-hand side. Right? And then we get a function of Y as a function of R, right? There is a left-hand side, it contributes to the transfer function. What right-hand side contributes is the denominator, as usual. This +1, as before, is from here. You can see mechanical derivations. No, express the thing in the Laplace transform form, substitute it, express Y as a function of new input. Notice it looks different now. It looks different now. What it means now is that if you're willing to treat this reference as a single time function, you don't want to, consider this v dot v as separate sort of component of the same time function that actually goes into your motor, for example, right? If you just want a time profile, you don't want two components, then the way your system reacts to this input would be described by this transfer function, not the one on the previous slide, right? There is a difference. What you call your input matters, right? Because if you expect to study how your system reacts to your input, you need to know what exactly is your input, right? So in this case, a reference signal is just a time profile, R, which directly added to your feedback control. This R we would call the feed-forward component of the control, right? And this is a transfer function, 33. Whereas if our input signal was V, the signal with which we compare our output, then the transfer function would be 27. The point here is, since derivations are very simple, you can do them by yourself. There is no problem. The point here is not to show you the formula for memorization. The point is for you to understand that what you need to do is basically decide what is input, what is output, and then derive. And then you get those derivations. But also notice that in both cases, we have the same denominator. That is quite significant. We're going to, the fact that it stays persistent in both cases has to do with the fact that feedback component of the control law was not only the same, it didn't have to be the same. Like this H, can, doesn't care of the particular form of your control feedback control, but it is a proportional control proportional to your state. That is important, and that is almost universal. We're always going to see this. That is why we have this guy downstairs. Okay. Next class, we will see how it influences our stability, our way of thinking about stability. The fact that we always have this guy downstairs in this equation. Okay. Now, this is good. We have a little bit of time. I think 20 minutes, right? So I'll use this time to give you a little bit of sort of additional information, which would be important for the next lecture, but also is basically would be like a key use case for Laplace transform in the era before computers, right? In the era when everything was done by hand, what you are going to see right now is going to be one of the key use cases for Laplace transform. Right now, it is not because we have computers, but it used to be key. It's still important for derivations, but right. So before we continue, a few more Laplace transforms. I'm not going to derive them. I'm just going to give it to you. So Laplace transform of this equation, e to the power at, is going to be like this, 1 over s minus a. In many textbooks, you'll have a minus here and plus here. It doesn't matter, right? It's the same thing. But I chose to do it like this. Later we can discuss why. All right. Here's another one. Laplace transform of a cosine. It is s divided by s squared plus omega squared, cosine omega t. Sine omega t gives us almost the same expression. The difference between the two is that for cosine we have s upstairs. For the sine we have omega upstairs. That is all. Finally, a quite complicated expression, e to the power at times a cosine omega t plus b sine omega t. This you can recognize as a solution to differential equation with complex roots, right? Laplace transformation is complicated. As a, s minus a plus b omega, s minus a squared plus omega squared. Looks like a combination of those two, which it is. That is all there is to it, is a sort of combination of those two. I mean, I guess that's not all there is to it, but it is quite close to the truth. Right? Okay. So that is our functions with which you want to work. You don't have to memorize it. It's just important that you see that those are the forms, fractions. That is first order fraction, second order fraction, right? And the first order fraction leads you to this type of thing. Everything else leads you to trigonometric style answers. In this case, also this. Okay, all right. Now, also Laplace transform is linear, as I pointed out before. So Laplace transform of a linear combination is a linear combination of Laplace transforms. Okay, good. Now, why is it useful? Well, to see why it is useful, we would need to learn what is a partial fraction expansion. Right? That is the stuff that you could have learned in a course which deals with polynomials. I have some doubts that there was anything like that in any of your math courses, but it is not complicated and we are not going to spend time on doing it by hand. So it's going to be easy, don't worry. So let us consider a transfer function, g of s, with a numerator n of s, denominator d of s, and both represented as rational polynomials, right? So we have a polynomial of s in the numerator, in the denominator. Now, in a simple case, when denominator has only real non-repeating roots, right? So all roots are real, none of them are repeat. By the way, those roots we call poles, rules of the denominator. They're called poles. Well, in this case, we can rewrite this expression 35 as expression 36, like this. Right? Let us see what happened. So this guy, I said it has real non-repeating roots. This is what allows us to write it as a multiplication of simple monomials, right? That is what allows us to do it. If the roots were complex, we would have to have a second order components in this expansion. If the roots were repeating, we would have had powers, right? But ultimately, it is not much more complicated. But for this simple case, it is like this. Now, if additionally, its denominator is a higher degree polynomial than the numerator, we can expand this expression in this form. Now, let us look carefully what happens. We take one of those guys, and we see it appearing in this simple polynomial fraction. Right? We take the next one of those guys, and we see it appearing in this simple polynomial fraction. And thus until the end, right? Until the last one. That is possible. That's possible. Now, the only question is, how do you find those guys, right? How do you find those guys? I guess you could also ask, how do you find the roots of the polynomial? But, we'll assume that we can find them, right? You would have software for that. Is doable. Is doable. So we would have the this style of expansion for this polynomial. Now, how to find those R1, R2, Rn? There's a process. The process, I'm not going to try to explain it here. It's like 3-4 steps of multiply numerator by this guy, cancel terms, and so on. Is easy enough. It is explained fully in the recommended chapter in the textbook, right? So if you go to the literature, you would find the first recommendation in the textbook, the chapter, and there will be like 5 pages explaining how to do it by hand. You don't have to do it by hand. You can also call a function Python or MATLAB, right? So those R1, R2, Rn. So it's possible to find them. I think that is good enough for right now. So polynomial of this type can be represented in this form. Okay, all right. Why is it good? Why do we care? Well, for today, I will give you one answer. We care because we can make an observation. So this Laplace function, right? This Laplace function is an image of the time function, like this, right? So the Laplace function is Ri divided by s minus pi. Oh, this is the same as 1 over s minus pi. We saw it in the 2 slides ago. It was e to the power pt. Right? R is just a coefficient. It goes in front of both like Laplace and time domain images. So this big F of s becomes this F of t. And instead of Ri divided by s minus pi, you get Ri times e to the pi t. Why is this very exciting? Oh, because we take this guy and it becomes this guy. We take this guy and it becomes this guy, right? So we take our Laplace representation of the differential equation, if you will, and we put it back into the time domain. And what we have, it looks a whole lot like a solution to this differential equation, right? In a sense, this is a way you could solve ordinary differential equations. You can put them into Laplace domain, right? Do fractional expansion. You get a lot of very simple terms. Each of those simple terms can be easily converted into time domain. You get your solution. That is very good. There are, of course, multiple details there. And since we're not doing differential equation course, I'm kind of skipping over them. But please remember that there was an assumption about initial conditions, right? There is additional things that I did not discuss, which is, your integrals in the Laplace transformation are always from 0 to infinity, right? We do never consider negative time in any of the Laplace related things. So your solution, your differential equation, everything, we are only allowed to think about time which is bigger or equal to 0. Those and similar considerations are there. Also, you would have to, be careful about what exactly you're trying to solve. Laplace transformation works, Laplace representation works really well for systems with input, right? So if you have a system with an input, you transform everything, including input. You do partial fractional expansion. You get a solution to the differential equation with the input. So basically, you get a particular solution, what we call particular solution. Those are the details, right? We live in computer age. For us, it is not very important to be able to solve differential equations by hand. So this looks like old technology, which was important in the 80s. Now it's not very important, right? But while that is very much true, this is going to be key for the technique we are going to see next lecture for a new type of stability analysis, which works really well and requires this type of knowledge. So for now, this technique is just a way to solve differential equations. Very pretty, very easy. But tomorrow it is going to give us, next week, it's going to give us additional tools. Okay, so please accept it. Do not try to erase it from your memory just because of this old technology. Okay, now a little bit more. As I said, not every equation would have the non-repeating rational real roots. So if you have non-repeating rules but with complex, some of them are complex, right? So when I say some of them complex, what I mean is you have roots which come as complex pairs, right? Then your denominator would be able to be represented in this form. This is your monomials that are related to your strictly real roots. And these are binomials, right? That's how I call it. Second order polynomials, which are related to your complex roots. Okay. Now, more general situation. Now, I also made an assumption that denominator had a higher degree than numerator. Now, let's drop this assumption. Let's assume that it is low or equal to numerator. What do we do? Oh, we can always just divide numerator by denominator until we enter, the what do you call it? Whole part of the division by the division would just become not a fraction but a simple polynomial, right? So after division, you would get this guy. It would be just a polynomial in front of your fraction, right? Just to give a crude example, s cubed divided by s squared, s cubed divided by s squared would be just s, right? It would be just a polynomial. So you can do it here. You can simply divide your numerator by a denominator. You will get a new numerator. It will be, in this case, we would call it m of s. And you'll have your old denominator just as before, right? Now, you would still be able to get your expansion. Your expansion, there is no reason to expand this guy. So the polynomials that you get by the division. But you also can expand everything else, right? So your fraction. So expanding your fraction, what you get is those same monomials related to your real roots, but also you would get this fractions here with a second degree, first degree numerator, second degree denominator, right? This will be related to your complex roots. Good to know. Good to know that you can do this kind of stuff, right? Now, why is it good? Well, basically, this guy can be represented in this form. That's fine. How to find these coefficients? I again leave it out, but you can figure it out. Like if you can take this expression, put it in the form represented in the table, you would see basically it. You would be able to put it in exactly the same form, and then from there you get a b coefficient and a small a here. That's it. If you wanted to solve it by hand, like differential equation, that's what you would do. And the typical exercise of doing this kind of stuff is like half a page of like calculation, maybe like 1 page of calculation. First you do expansion, then you convert your second order fractions into form similar to what is in the table. Then you convert it into this form here. That is your solution. Sometimes if you're lucky, it will be pure sine or pure cosine, even better, right? Okay, so that is the way to solve differential equations. So while I didn't present you the case with repeating roots, you can just trust me that it would also be handled naturally. The fractional expansion would have squares or cubes or whatever in the denominators. It would still work, right? Now, in case you will have to do it, in case you have to do it, here is the automatic functions to find your coefficients for you. I think I'm not sure if educationally it is best to start with this or if it's best to start by hand. Maybe it is best to start by hand if you have enough time, right? But if the question is whether or not you will do it at all or do it by computer, then do it using computer. Yeah. So in case you want to perform this operation and test anything, it is very easy to do using automated tools. Like residue is the name of the function. It's not called expansion or anything. It's called residue, both MATLAB and Python. Right. And I think that is it. Now, this is the recommendation I was talking about, this chapter. There you have step-by-step instruction of how to compute fractional expansion for real roots, repeating real roots, complex roots, how to do inverse Laplace transform, all of that. And there are a lot of examples. So please, read it, consider it, and so on. There are also very nice YouTube lectures by Brian Douglas. A lot of people who are interested in control praise them. So just in case, it may be a good supplement, right? But for fractional expansion, I think NIS is the best source to go to. Now, next lecture, we're going to take all of these tools and tackle something that is maybe the key use case for transfer functions and Laplace transform. Namely, we're going to try to understand how equations react to inputs. Right? So far, we only discussed the fact that inputs exist, reference signals, other stuff. But obviously, you can imagine inputs matter, right? if you drive a car recklessly or if you drive it very carefully, there will be a tremendous difference between how the car behaves. It's the same car. The control system inside the car is the same control system, but reckless driving can make the car flip. Good driving will allow the car to go from point A to point B. Same about airplane, same about almost anything. Input signal matters. So next lecture and a half, in fact, more or less 2 lectures, we're going to study it. One of the tools we're going to study, going to use is border plot. Is completely dependent on information from this lecture specifically, but we'll study more than that, right? So I hope we next week we're going to have interesting stuff for you to see. That's it from me. If there is any questions, then I'll be happy to answer. I'll stop the recording so in case you can ask after.